Okay, thank you very much for your presentation. I was just intrigued about the slide with the New Zealand, the money you spent and you were able to convince the New Zealand government to build a center. The question is, how are you able to convince the government to build a center with all that amount of money?
The key thing was we already had a history, and so we were able to actually point to the fact that we already, as a nation, punched above our weight. So we had the legacy of Dan Walls, Crispin Gardner, and so forth, and we were able to point to the people around the country that were already doing things in this area. And then we were able to suggest how we could take that forward into economic benefit. And the government took a punt on us, I guess. They actually believed us, and they realized that internationally there was a high respect for New Zealand. New Zealand clearly had this ability, and they believed that we could turn that into economic success. And over the next 10 years, we actually generated a number of companies, and we actually generated some economic return on that. We were also generating research income through other agencies where we were clearly showing that we were leading researchers in the country. And so you need that sort of kernel around which to base something. And again, it comes back to, hey tangata, it's people, right? You need to actually find a kernel of people that you can build something around and then grow something. And ultimately governments want to see return on investment, and so you have to make the investment case. That's as far as I can see, the only time you actually have success is when you can say there's going to be a return on investment here. You're not putting money into the National Ballet, right? This is not the things that it's nice to have as an economy. These are the things that are going to grow the economy and allow you to do other things. That's the key argument.
Right, and I think there is a figure for the return on investment on average around the world, right? I mean, it's every dollar put in or euro produces something else a little bit bigger for the economy.
Absolutely, like that. But that's true. Like I'm the director, I'm the chair of the board of a museum, and we make the same arguments around the investment in the museum. It returns in terms of our local economy through tourism. But like everyone's going to be making the same arguments, but what you want to be making the argument around is your export economy, and it's the high value elements of your export economy that you have to drive. Like that's what's going to actually change the bottom line for your government, and that's what ultimately they want to invest in.
Great. Okay, we got another question, and this is the last one because.
Good morning, and thank you for your talk, very insightful. So my question is centered about the people aspect. So considering the fact that, the saying you said, it's the people, right? And Australia is a diverse country with a very rich demographic of people. For example, you mentioned the Maori people and all that stuff. So my question is kind of about how you see engaging people from specific social, cultural contexts in a manner that will pique their interest in quantum technology, for instance, not necessarily applying maybe a one-size-fits-all, and I'm sure maybe you may have already addressed it in your slides, if I'm not mistaken, but, kind of looking at educating the people to pique their interest in a manner that you think is relevant to their context. I don't know if that is in the pipeline, or, you know, if it's something that you're considering or have considered in the past. So I would like to learn more about how maybe you're approaching that.
That's a really good point. If Joe's going to give me a long enough time, I'm going to have a little anecdote here.
Okay.
I went on sabbatical leave to Paris to work with a friend, Ivan Castan. Ivan is a very formal French mathematical physicist, and I'm like my supervisor was a student of Phil Anderson. I grew up in a very sort of model-based sort of like, how does this work? Like, let's form a sort of picture and we'll fiddle with it and then we'll form the mathematics afterwards. Whereas Ivan was a really, really formal French. I'll write down the mathematics and deal with this. And so I went to work with him because it was a very different way of doing physics, and I really enjoyed learning from him, and it was a very deliberate thing on my behalf to go and learn from him. And my point is that if you're a hammer, everything looks like a nail, right? And when I look at the people across New Zealand that I work with in terms of the Maori population or anyone else, like, I would like to bring their perspective to looking at a physics problem before I've indoctrinated them with my way of doing physics. And I think that's one of the things that's really important, is that we embrace the perspectives of everyone so they can bring how they view a problem to science, and otherwise we're sort of cutting out a whole way of looking at science. And so there's lots of opportunities there to embrace different cultures, different ways of looking at things, different pasts. And that's a particular thing that we're facing in New Zealand, with understanding Mataranga Māori, which is Māori indigenous knowledge, and how that can actually be influential within the science that we do. And Australia, which is a very different country, by the way, but Australia is going through the same sort of processes with its indigenous knowledge and relationships with indigenous populations at the moment. So there's a whole bunch of things that we have to deal with there, but I think there is a whole precedent there, I think, actually from our own interactions across cultures. The way of doing physics in Russia, France, the United Kingdom was all very different, and we all actually can learn very, very different things from each other. One of my heroes was Freeman Dyson, who took the work of Julian Schwinger and Richard Feynman and showed that they were actually formally equivalent, even though that they're very, very different approaches to doing physics. So, you know, like there are all of these wonderful opportunities to do physics in different ways, and I think that's something that we should embrace, enhance, and look for in different cultures.
Okay, well, let's thank David again for a really wonderful talk. Thank you, David.
Yeah, all right. Thank you.
Thanks for staying up. Okay. All right. So next, where's Henry? He's somewhere around. Okay, so Henry Martin is, you all know Henry, but anyway, he's from KNUST, the lecturer in the Department of Physics, and coordinates Mathematical and Computational Physics Unit. He's actually been to Rome Sapienza, so he probably is missing Italian pizza quite a bit. But his research focuses on digital twin approaches to real-world problems through multi-physics modeling, machine learning, and statistical analysis. So it really spans many areas: water systems, aerodynamics, renewable energy, and materials science. So he's going to talk about the state of quantum science and technology in Ghana, addressing the quantum divide and ensuring inclusiveness for all through the SDGs. So, Henry. You get that.
All right. Thank you very much, Joe. And I would like to first of all thank the organizers for making this possible, and as well thank all the MCP units and all the international collaborators that made this possible as well. So I'm going to try my best. What I'm supposed to do is to tell a story, but as academic as well, we always give presentations, so I'll try to combine the two. The only thing is that I'm not sure the 30 minutes is enough because there's a lot going on, but I'll try my best. All right, so I'm Henry Martin, just as Joe said, and I'm from KNUST with the Mathematical and Computational Physics Unit, and I'm here to deliver the state of quantum science and technology to address the quantum divide and then promote the inclusiveness. Okay, so quantum basically we have known as a pivotal course in physics programs and in most of the specialized programs in mathematics, as well as of chemistry, computer science, and engineering have been taking some of these courses. And in quantum mechanics, we have been taught certain concepts like what we know as the many-body problems. And these many-body problems have been solved approximately using some kind of techniques. And these techniques basically are in the form of Hartree-Fock's density functional theory and so on and so forth. But more of it now is looking at some other concept, which is the superposition and then entanglement and others. This then has led to the quantum science and technology, with then we have the quantum computing, which looked at the development of algorithms, and then we look at software and then hardware. We have the quantum communication, we then look at the ensuring of network channels through encryptions and all of that. We have quantum sensing and meteorology that then looks at the measurement and controls. We have the quantum material and so on and so forth. I believe yesterday, most of you heard a lot about that. Now, in the global landscape, there has been a lot that is going on in terms of the improvement and in terms of development. And we have seen across the continent that in Europe and in Asia, they have been, first of all, been able to build quantum research centers. A typical one which we already know is the center in Canada, where they have Parameter Institute, Waterloo, and so on and so forth. They have also been able to come up with startup or companies that are bringing in development in these regards. And we have so many of them, like IBM, we have Unitary Fund, we have IQM, and so on and so forth. They have also been able, continentally and nationwide, come out with national strategies that they intend to employ, that in this number of years, this is what they intend to achieve going forth. But the story in terms of Africa is far, far different from that of the global world. And so in Africa, what are we looking at now? For some time now, I think just about a month ago, the African continent community met in South Africa and decided to come together and try to build this kind of alliance, which is called the African Quantum Alliance, for short, Africa. And their idea is to get everyone in Africa together so that they will be able to realize how to push forth the quantum development in Africa. Again, in our brothers in the diaspora has also been able to form what we call as the African Quantum Consortium, which is a very vibrant group, and they are trying to push for the advocacy of development of quantum in Africa. Notwithstanding these two groups that have been able to push these frontiers for Africa to realize its fate, South Africa, on the other hand, has done so well. As we speak, I mean, in the past 15 years, they've had several conferences, they've had several breakthroughs. They have a couple of centers, a couple of quantum centers. They have also been able to come up with their quantum science and technology strategy. And they are working in quantum computing, they're working in quantum optics, and so on and so forth. Our other friends in Tunisia, they also have quantum centers. They've been able to come together as a people, as a network, and they are also working in quantum computing and so on and so forth. Morocco, on the other hand, don't have a center yet. They are doing some research, which is in the quantum key distribution. They're looking at some kind of quantum optics as well. And Egypt, they have a bit of research ongoing in quantum computing and quantum key distribution, but they are yet to start up some master's program in this regards. Now, the big question I believe we are all waiting for is Ghana. What is the state of Ghana? Where have we gone to, and where do we find our feet in now? Now, before I go to Ghana, I would like to just say something briefly to clear the air, that most of the African countries, or most of us here, are really into the classical simulation of quantum systems, where we are using some machines to now determine, like I said earlier, or in terms of the Hartree-Fock, DFT, and so on and so forth. Now, this we do in using the CHPC in South Africa, which you can see the map there, green, and then the slash red and blue are the countries that are involved in using these CHPC resources. And Ghana, as you see there, is the only West African country that is involved in this. But again, like I said, this is in the classical simulation for quantum systems. Now, even though we are part of it, we see that we are having about 33% of the programs that are using these resources. With the 33% of programs, you can see on the underhand side that we are having more than 50% usage across all this. And so it means that Ghana in itself is doing a lot of work when it comes to this classical simulation of quantum systems. And for this nodes, they have about 100 nodes. You can see at the top there that is at every time t, it is fully used. Apart from that peaks that drops, which are due to maintenance and all of that. And so this actually gives some kind of a queuing in terms of the job that we use. Now, Ghana in itself has about 16 traditional universities in the country. We have about 10 private technical universities and about 24 chartered private universities. Among these, we are having 6 main universities that are involved in some activities, both in the classical simulations and that of the quantum simulations. Now, I would like to start with the University of Ghana. And the University of Ghana, at the Maths Department, we have a group doing something in quantum gravity. And then at the Physics Department, they're also looking at the classical simulation of quantum systems. Now, in the University of Development Studies and that of CKT Kandam in Applied Technology, they are also looking at the same thing in terms of the classical simulation of these quantum systems. When we come to University of Energy and Natural Resources, the Computer Science Department, they have a group there looking at quantum machine learning to understand the stock exchange, that is the finance systems. I'll go deeper into those opportunities for us to understand them now. Now, in UCC, the physics department in 1992, Professor Alote here was able to establish them a photonics lab. And so they have been dealing with photonics since 1992. You can see that. They have started something all the way since 1992. And that is their LAFOC lab. And in recently, I think in 2023, they had accreditation, which they established the the computational thinking lab. This is a lab with about 20 nodes of computers to do classical simulations again. And then we come to KNUST. In KNUST, we have several things ongoing there. So we have the engineering department, which in recent days, they have started some training in having to go into quantum telecommunication in terms of having to look at the encryption. We have the chemistry department that looks into computational chemistry. And it was set up in 2010. the quantum, chemistry lab in 2010. And so they too have been doing something for quite a number of time here. The maths department, as of last year, started looking also into quantum algorithms that they will also use to understand our markets, that is our financial sectors here in Ghana. When we come to the physics department, I'd like to thank some people here, that is Robert. I think about 2023, they start to have some frontiers in light, and these have been able to generate some discussion, and they are about building the photonics lab in KNUST to look into characterization of materials. Then we have the mathematical and computational physics, which I'll dwell more in later to let you see how a pipeline can be developed. Now, this discussion that I have done here follows these decisions, which then you can see is an onion diagram, and then the first one tells you the level or the intensity into which we are undertaking some development in this area. The first one, which has to do with quantum experiment or quantum technology, is the main reason why you see that as the very least is that there's very limited experimental infrastructure, either to even start it up or to even maintain it going forward. And because of also the cost, and that brings me to the question I was asking the earlier presenter about how they are able to convince their government to do that. And so we as a country, we fall short very well in that area. But the second one, which has to do with the quantum computation, is an interest that is really booming up in these recent times, where we see most of our young men trying to go into quantum algorithm and trying to go into quantum machine learning. And that comes to the third one, which is the classical simulations, as I mentioned, is very, very intensive across the whole countries. In fact, if you look at the universities, as I mentioned, all the 6 universities, there is some form of classical simulation of quantum mechanics. And in terms of the theory, all physics programs, undergraduate levels, postgraduate program, does some physics. And in some mathematics department and chemistry and engineering, they do some kind of quantum mechanics. And so that is very wide across the nation. Now, so where do we stand, which is the reality check for us here? Do we have a center? Do we have a startup and all of that? And so with the brief thing I've said so far, we can see that, well, we don't have a national quantum strategy yet. But I believe, just as the presenter said, we have to get the people together. It's about the people. People are important, just as he said. And so bringing the people together, we may get there. Again, he said about the center, and that was why I was asking the question. So that before I come here, I think you know the answer to all the questions I'm asking here now. Okay? So, yes. So we don't have a center yet. We are already teaching quantum mechanics in all our programs. We don't have any setups yet or companies that are into, but yes, we can make them happen, and I'll show them as I move on. In terms of research, I've told you about 80% is into the classical simulations. There are a few doing some quantum algorithms and quantum machine learning. And so Ghana as a country, and we as a people, this clearly shows the divide that we have with the global landscape, and then the divide that we have even among us in terms of our African country as well. And so we have to find a way as scientists to be able to solve a problem. As scientists, we look for a problem and then we solve the problem. That is what we are trained to do. And so the problem in having to solve is what we're looking at is as a big idea. And the big idea is for us to have a national quantum science and technology strategy. And we believe that this is a startup that most people are here discussing and trying to bring up something that this can be able to go on. And in doing that, we should be able to have cluster of center of excellence, which we call in the ARC-QST. And so we think that this is possible, and this is possible through an educational and research pipeline that we ourselves have undergone through it as a means which I intend to show you using the mathematical and computational physics unit model. And so in showing that, I'll start to tell you that we started this in 2020 by having an accreditation from GTech, with the physics department and KNUST. And the whole idea is for us to be able to build capacity. But as we all know, and across the whole of this week, there have been a lot of problems or a lot of challenges why this is not possible. And so what are the challenges? And we have the institutional, we have the student-owned challenge, we have the government and the industry. Of course, we as the institutes or the institutions, we face challenges as funding. The critical part is to fund. How do we fund everything we do in the university, including our resources? Lab is not, we are unable to fund the lab because of the equipment. We are able to fund the personnel, to get a lot of personnel to come and teach or to undertake research. And getting a lot of personnel then will mean that the workload in having to teach will have to reduce. But then we do not have that as well. And then on the student side, when you move back down to the senior high secondary school, it's rather unfortunately I'm not here this morning, but if you go to the senior secondary school and you ask the student, how many of you even given the opportunity to come to KNUST to read physics? I tell you, you can get 1 out of 100. In fact, we have done that severally, and I'll show you, we move to schools to have an outreach on that. And so that is also a problem. And in the other side as well, in most of our education levels, from the senior high school to the university undergraduate and then postgraduate, the transitions, how do we deal with this student? How do we get them to really do something? And then the funding for the student. Most of our students, and I believe everybody here is already aware, that most of our master students are working. And so the question now is if you are working, which is a full-time, and also undertaking your master's degree, do you have a lot of time to concentrate on research that can yield something out? These students have to work because they have to pay for their tuition fees, they have to look for their accommodation, and so on and so forth. And then the job market, which then is connected with the government and then the industry. The student then finish the physics course, maybe quantum, and then he gets employed where? Nowhere. Because there's no connection with the industry and the academia, so that we can be able to bring something out. But these are challenges. Scientists, again, we are supposed to solve challenges. And so that is where we start as our footstone in having to solve this challenge. And so how do we solve this challenge? First of all, we decided to move to the high schools to do an outreach program. We decided to do an open day program for the high schools even to visit us in the school, in our university, so that they see what we have, and then they can liken it to everything they do, and then appreciate what we are doing in the university. And so that is where we started in having to resolve the interest of the student. Then in how to do the transitions, we have a collaboration with some of the partners that we can have transitions. You finish your bachelor's, you can be able to take some online courses, you can be able to take some residence courses together with our partners, just that it brings you to the level of the graduate program that you wish to undertake. And this we're doing with Parameter Institutes. And then in terms of how do we go by the funding, or how do we go by the resources? This I remember in 2020 when the GTech committee came around to ask. They were like, are you sure you can run this program? How do you intend to fund the student? Because you want a full-time student. Then we were like, well, we have a model, and the model is for us to be able to have an exchange program. And this we started with University of L'Aquila. They gave us an MOU, we signed an MOU and all of that. And so that was presented, and we have exchange students with our partners. And in this time around, we have partners, they spend some time here, they spend some time there. And so sometimes we have an online, they teach them online, and so on and so forth. This is able to handle the challenges that we foresaw earlier. Then in having to link with the industry, the concept was that if you have students and you are training the student, sometimes it's difficult getting the funding from an international partner to do what you have to do that is pertaining to the social needs. But the only reason you can do that is when you get in touch with the companies and then you bring out the problem which the international partners have an idea about. And so I'll brief more about that when I get to the centers. Now, in doing all of this, we need to be able to set up conferences and workshops like this. Conferences and workshops that can be able to fund students from other regions, not just in Accra. I mean, if we have funding, students can come over from the north, from Kumasi, then they can be able to attend the funding, have discussions to see their reality. This we started way back in 2021 with One Quantum Ghana. I believe most of you have not heard of that. But One Quantum Ghana, we started this in 2021. And then in 2023, we went on to do the Quantum Aquaba. That was the first Quantum Aquaba we had, which was hybrid, in person and then online. And then we move on to some online other ones. There are other ones that the team is actually planning on. At the appropriate time, I believe most of you will be sent an invitation to join this conference. It's for us to harmonize and think about the country in moving forward with the country. Now, the vision for the big idea stands in terms of what we call the ARC-QST, as I mentioned earlier. This is the things that in having to undergo in the route of quantum science and technology, we may be able to segregate in terms of the onion diagram, where we saw the weaknesses. And so with the weaknesses, we can be able to segregate it into 3 parts. A 3-part having to deal with the mathematical, which we have to do some formulations for our algorithms. And the other part has to do with the computation, and the other part also has to do with the experimentation. These together, we're proposing the 3 centers for Ghana in the sense that, well, one center is already established, which is the AIMS Ghana. Their mandate is to come out with mathematical formulations, and that they are already doing well in that. And so what we are really left with is to look at our computational and look at our experimental. What are we doing or what can we do? And so we have the Calc Ghana, which is just Center for Applied Computation. That is the Calc Ghana, looking at all the simulation of these classical systems, including quantum system, algorithms, and so on and so forth. Where the Equate Ghana deals with the experimentation, the hands-ons. Because one, you cannot do computation without understanding the experiment. I mean, physicists, we always start from going to the lab. In our university, you do 2 years of lab work because you need to understand the fundamental physical phenomenon before you can do anything else. Other than that, it becomes like a black box. And so these are the 3 centers that we believe can be done. And the centers follows the pipeline which I described, or the model that I described that was centered on the MCP, because then there are challenges. We cannot sweep away the challenges that we have out in Ghana. We need to find a way to solve it. Others have done it. There is a plan to do it. So we can use the same way. We have the early identification of the students by going to the SHS, improve their interest. We have the integration of the NSS by having some transition plans and all of that. And then we have the funded MPhils and PhDs, so that with your exchange programs, I mean, there are so many international collaborations. Yesterday, you heard from Imperial College. They are willing to collaborate with all of us here in Ghana. This is a way for us to have exchange programs across. And then to have postdocs. Postdocs, in most of us, we know that in our governance settings, we cannot have employment from PhD straight away. Sometimes it takes a year, sometimes it takes 2 years before the government approves. I finished my PhD. Do you have to wait for the government? You need to be engaged in doing something. Some of us had the ability to travel outside the country to go and do something before employment comes. We can still employ the people here in our centers to do research work for the country, for the society, as postdocs. And that can be one of the opportunities. This can lead into what we have as the research base, the relevance of our research, what we can do. And that turns out to train more people for both the academia and that of what? The industry. Yearning to bring up the startups and the companies that the other global companies are already having. And that is the pipeline for that. And this can come out with any particular organogram where we can have the stakeholders in terms of CSR, GAEC, and all of that, being part of the chain in the sense that we have the QST with their 3 main centers and the universities. Already, every university in Ghana is undertaking some kind of research, either classical or quantum, but they may have to fall in certain aspect of these centers because you cannot rule away the university research out automatically because every researcher or every professor is employed to teach and also do research. It's part of it. And so as the centers, we have to be able to bring the people together. We have to be able to get everybody together to be under some specific center, to have to communicate, to know what they are doing. Then there's a plan, either biennial plan, 5 years plan for the country doing something which is related in this thing that we look at. One thing I always have to look at as well is it possible? I don't know why centers should be able to teach an undergraduate program or teach a master's program. As far as I know, in most of the world, the centers are created for the research-based. And so, as I put a note there, centers are not supposed to be a taught master's program, but intensive research-based to see the development of the country. This can be discussions that can start in terms of having to solve our issues in quantum science and technology. And so then brings us to our strengths, our weakness, and all of that, and the main goals, which falls under this, this diagram here in terms of training more people, training more staffs, getting them to do something, becomes a cycle, coming back to the university, coming back to the industry, and then bringing up a lot of startup. Many people say that in other countries, the PhDs and all of that are going into companies because they have been able to raise a lot of people. And there are a lot of people who have a lot of knowledge to set up their own company and then be able to bring in improvement. And then the economy goes up. And so that is the cycle. And so if we are able to follow these forms, we'll be able to look at something. And we believe that, again, in 10 years, in 2035, that is to say in 10 years from now, we should be able to raise more people for the country. Because we started this in 2021, we had accreditation with just 2 students, 1 PhD. Now those 2 students are done, they are coming to do their PhD, the PhD will be completing soon. And so that is to say that is about 4 years now, next year is 5 years. And so to do a calculation and postulate in 10 years, if you take in more students, more than 2 or 5, you could have a lot of students, and this would be able to come back as generating economy for the country. Again, the speaker said, the relevance, the economic benefit that the country can have. And that was why I posed that initial question, for us to all to have our solution. Some may say, how do we get this relevance done? How do we prove to the government that classical simulation of quantum systems or quantum system is important? What can it do? There are so many aspects that are ongoing in some of the universities, as I mentioned, and also in KNUST. Quantum finance is there, as I've mentioned. Some people are already doing it. Drug design in chemistry, they have been doing that for some time now, for pharmacy and healthcare. We have water. We ourselves in the physics department, we're looking at some things in water. And I'll show you how this is being done. For the quantum finance, I can speak of what UNER is doing and what they are doing in KNUST in the maths department, trying to understand the stock exchange, trying to understand our financial markets, to come out with algorithms, which then based on quantum optimization, optimizing the chain that works. And so that is one key simple thing that we as Ghanaians would be able to do using quantum to do. And the other ones are also there that in the future we can be able to look at. And when it comes to water, as I mentioned, in KNUST we're looking at this in terms of the digital twin, trying to monitor our water. Yesterday the lady spoke here about contamination, and it is general in Africa. We have contamination based on agrochemicals because of pesticides. We have contamination because of unused. I take my paracetamol, some is left, I just put it in the dustbin. It goes back to the gutters. Contamination is there. We have contamination based on liquid waste. we have contamination. And so the cycle of our water, there's contamination. Treating it is real time. How does quantum come into all of this? We have other ways. We're looking at quantum modeling of water in terms of using the treatment. We can develop crystal porous materials and having to look at the treatment. We can look at the quantum optimization. The whole water chain system can be optimized in using quantum. Quantum sensing and meteorology. One of our students will be visiting Germany in October in a research University of Bonn under the quantum meteorology. And these are some of the things that we can look. Yesterday, someone mentioned that, is that possible we can have a lab? Yes, that is one of the things we are also looking at. Developing an online lab so that you can be able to have all the optics that you can do. And it is also one of the things that we're having with the University of Bonn to develop some kind of techniques around that. And so this is with the chemistry, which they are looking into the drug and healthcare delivery. And all of this fit into the SDGs that we have been discussing all this while. We look at SDG 4, 8, 9, and so many of them. Partnership, healthcare, water, they all fit right into the discussion. I'll end my story here. I believe my time is far gone, but I think I have done some storytelling. And so, yes, we are not there yet, but we can get there. Together, if we can all come and sit at the table and discuss the way forward for quantum science and technology. The people, the government are one. Thank you very much.
It's on now. Thank you very much, Henry. That was really wonderful. Okay, so time for questions? Yeah. I imagine there'd be lots of questions.
All right, Prof, thank you so much. I think you've opened our eyes into so many areas that we weren't aware of it. But my problem goes with the teaching of physics. I think the fundamental is the basic level. Yes, teaching of it is a little bit difficult. And I think the teachers are not coming close to the student for better understanding. So fundamentally, we fear it before we go to secondary school. So by the time you reach secondary school, physics becomes a blow. When you see it, you run away out of it.